For section 4.5, we are given an equation. We're going to find the domain, y-intercepts, symmetry, asymptotes, where it's increasing, decreasing, the max and min, the point of inflection, where it's concave up, concave down, and then we're going to use all of that to graph it. So starting all the way at the top. So our equation is y equals x cubed minus 3x squared. So our domain, it's all real numbers. The y-intercept, we can find this by setting it equal to 0. So we have 0 equals x cubed plus 3x squared. So we can factor out an x squared. So we have 0 equals x squared times the quantity x plus 3. So when we set that equal to 0, we get x equals 0 and x equals negative 3. So those are our two y-intercepts. So where it crosses over. And then we have symmetry. There is no symmetry with this function. There are also no asymptotes. And then we're going to use our first derivative test to find out where it's increasing and decreasing. So the derivative of this equation is f prime of x equals 3x squared plus 6x. And then we can factor out, well, we're going to set equal to 0, and then we can factor out a 3x. So we have 3x times the quantity x plus 2. So then we end up getting x equals 0 and x equals negative 2. Then we can put that on our number line. And we have our point at negative 2 and our point at 0. So we're going to test points in between. So let's say negative 3, negative 1, and 1. So at negative 3, we have it, if we plug it back in, we have negative and a negative, so we have a positive. If we plug a negative 1, we get a negative and a positive, which is negative. And for 1, we get a positive and a positive, which is positive. So this means we are increasing from negative infinity to negative 2 and from 0 to infinity. So we're going to squeeze that in here. Negative infinity to negative 2 in union with 0 to infinity. And then decreasing is just from negative 2 to 0. So decreasing negative 2 to 0. And then we're going to find our maximum and our minimum. So we already have our points. We just need to plug them in. So we're going to plug in negative 2, so f of negative 2, and then when we calculate it, we get 4. And then f of 0, plug that in, we just get 0. And so we see that our maximum is at the point negative 2, comma 4, and our minimum is at 0, 0. So then we use the second derivative test to find our point of inflection and then to ultimately determine when our graph is concave up and concave down. So if we take the second derivative, f double prime of x, we get 6x plus 6. Set equal to 0. We can factor out a 6, so then we just have 6 times quantity x plus 1, and then when we solve that, we get x equals negative 1. So we're going to put that on our number line to test it. So negative 1, let's say we're going to test negative 2 and 0. So we plug these in from negative, when we plug in negative 2, we get a negative number, plug in 0, we get a positive number. So then if we plug in f of negative 1, we end up getting 2. So then our point of inflection is at negative 1, comma 2, and our graph is concave up from negative 1 to infinity, and it's concave down from negative infinity to negative 1. And then we're going to go ahead and graph that. So first, we're going to graph our max and our min. So we're going to go by intervals of 2, so 1 squared equals 2. So our maximum, so 1, 2, 1, 2, 4. So here's our max. And our minimum is at 0, 0. And then we're going to go ahead and plot our point of inflection at -1, 2. So that is right here. So then we can look here and see that our graph is concave up from -1 to infinity. So we can connect our point of inflection with our minimum. And we can extend that out to positive infinity. So we have our graph is concave up, and then we can connect then from negative infinity to -1 is concave down. So we connect our point of inflection to our maximum, and then bring that down to negative infinity, so it's concave down, and that's our graph. For our second example of this section, we have the function y equals x minus x squared over 5 minus 6x plus x squared. So to find our domain, we're going to actually take it and we're going to break it apart a little bit. So we are going to have y equals x times the quantity 1 minus x all over 5 minus x and 1 minus x. So we see that these two actually cancel out. So we have a whole at x equals 1. We can also see that when we plug in 5 for x, we get 0 on the denominator. So then we also know that x cannot equal 5. So we have for our domain is negative infinity to 1 in union with 1 to 5, then union with 5 to infinity. So this just accounts for the whole and the asymptote that we have. So for the intercept, this is easy. So when we actually have this, we just end up, when those two cancel out, we get x over 5 minus x. So if we set this equal to 0, we get that our x and y intercept are both 0, 0. So we have an intercept at 0, 0. We have no symmetry. So for our asymptotes, so since when we plug in 5, the denominator becomes 0, we have a vertical asymptote. So we have a vertical asymptote. So we're just going to say vertical at x equals 5. We also have a horizontal asymptote. So if we take the leading coefficient, so x squared over x squared, it's the number in front of it is -1 over 1. So then we have our horizontal asymptote at y equals -1. So we have horizontal at y equals -1. And that's just an easier way to find the horizontal asymptote. And then for increasing and decreasing, we're going to do our first derivative test. So we do have to use the quotient rule for this one. So we get f prime of x equals the quantity 5 minus x times 1 minus x times -1 all over 5 minus x squared. So this gives us is equal to 5 all over the quantity of 5 minus x squared, but it cannot equal 1 or 5. So we end up getting that it's increasing the whole time. So we're going to have increasing from negative infinity to infinity. And we're just going to write NA here. And then next we have our maximum and minimum. So since we don't have any critical points from this part, we're going to have no max or min. So we're going to have no extrema. And then concave up and concave down. We're going to do the second derivative test. So f double prime of x equals 5 times the quantity 5 minus x to the -2nd. Since it was on the bottom, we're going to bring it up to the top, and then the exponent becomes negative. So we have f double prime of x equals negative 10 times 5 minus x to the negative third times negative 1, because we used the chain rule there. So then we're going to rewrite this f double prime of x equals 10 all over 5 minus x cubed. So when we set this equal to 0, we get our zeros are x equals 1 and 5. So when we see this on our number line, we are going to have 1 and 5. So when we test the points in between, we have up, up, and down. So we have concave up from negative infinity to 1 and 1 to 5, because there's a hole there. And then concave down, we're going to have from 5 to infinity. If we go ahead and graph this, so we don't have any extrema, but we do have our intercept, so we can graph that at 0, 0. And then we know that we have a horizontal asymptote at y equals a negative 1. So we're gonna draw a dotted line to represent our asymptote, and then we have another asymptote at x equals 5. 1, 2, 3, 4, 5. So we're gonna draw another horizontal asymptote, and we're gonna go ahead and extend this graph just a little bit. So we have, what we're gonna do is, so we have concave up from negative infinity to 5. So all of this is concave up. So we're just gonna go ahead and sketch this. It's gonna look like that. Then our second one, extend this, is going to be the opposite. Since it's concave down, it's going to look like that, staying away from both of our asymptotes.